Dear students, I am Anuradha Rajesh. Let us begin with the last session of the chapter Light, Reflection and Refraction. After today's session, you will be able to draw ray diagrams for framing images using concave lenses. Apply the sign conventions used for spherical lenses. State lens formula and apply it to solve numerical problems. Define magnification of a lens. Relate the convergence or divergence of a spherical lens to its power. Before we venture out to frame images, let us have a quick recap of the special rays used for framing images using concave lenses. So, here we go. A ray of light from the object parallel to the principal axis after refraction from a concave lens appears to diverge from the principal focus as shown in figure A. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis as shown in figure B. And now the final one. A ray of light passing through the optical center of a concave lens will emerge without any deviation. Let us now try and attempt making the ray diagrams in case of a concave lens. First, let us consider an object placed at infinity. I hope you remember that an image is formed by either actual or apparent intersection of two or more light rays after refraction through the lens. Considering the case when the object is placed at infinity, the rays incident from the object are represented by a pair of rays parallel to the principal axis. After refraction through the lens, these rays appear to meet at focus f1 of the lens. Since the image is formed due to apparent intersection of light rays, it is virtual and erect. The size of the image is highly diminished or point-sized. Now moving towards the case when the object is placed anywhere between infinity and optical center of the lens, we shall consider two rays for image formation. The first ray, being incident parallel to the principal axis, shall appear to pass through the focus f1, while the other ray, passing through the optical center, shall move undeviated. The apparent intersection of the two light rays forms a virtual, erect and diminished image. Sign convention for spherical lenses. For lenses, we follow sign conventions similar to the one used for spherical mirrors. We apply the rules for sign of distances, except that all distances are taken from the optical center of the lens. According to the convention, the focal length of a convex lens is positive and that of a concave lens is negative. You must take care to apply appropriate signs for the values of U, V, F, etc. Lens formula. As we have a formula for spherical mirrors, we also have a formula for spherical lenses. This formula gives the relationship between object distance U, image distance V, and the focal length F. The lens formula is expressed as 1 by V minus 1 by U equal to 1 by F. The lens formula is valid in all situations for any spherical lens. Take proper care of the signs of different quantities while putting numerical values for solving problems relating to lenses. Magnification of a lens. The magnification produced by a lens, similar to that of spherical mirrors, is defined as the ratio of the height of the image to that of the height of the object. Magnification is represented by small letter m. If h is the height of the object and h dash is the height of the image given by the lens, then the magnification produced by the lens is given by m equal to height of the image upon height of the object equal to h dash upon h. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given by magnification m equal to h dash upon h equal to v upon u. Now it's time for us to solve certain numerical problems relating to lens formula and magnification. But before that, here are some tips for solving numericals. The object distance u is always negative. In case of lenses, the image distance v is negative for a virtual image, while positive for a real image. The focal length of a concave lens is negative, while the focal length of a convex lens is positive. Height of the object h is always positive, while height of the image h dash is positive for a virtual image and negative for a real image. I hope you will remember these tips while solving numericals. Why not solve some numericals ourselves? Let us start with one. An object 5 cm in length is held 25 cm away from a converging lens of focal length 10 cm. Find the position, size, and the nature of the image formed. Here, object size h is equal to 5 cm. Since the object distance is negative, it will be equal to minus 25 cm. As we know, the focal length of a convex lens is positive. So, focal length f is equal to 10 cm. In this case, we are required to find the image distance and the image size. Using lens formula, we will have 1 by v minus 1 by u equal to 1 by f. Rearranging the equation in accordance to our needs, we can have 1 by v equal to 1 by f plus 1 by u. Substituting the values of f and u in the equation, we will have 1 by 10 minus 1 by 25 equal to 3 by 50. V, therefore, will be equal to 50 by 3 centimeters. Hence, the object distance turns out to be 16.67 centimeters. As V, that is the image distance, is positive, the image will be a real image. Now, according to the magnification formula, m is equal to h dash upon h equal to v upon u. Substituting the values of h, v and u, we will have h dash upon 5 equal to minus 2 by 3. The size of the image can be calculated as h dash equal to minus 10 by 3 equal to minus 3.3 centimeter. Negative sign shows that the image is inverted with respect to the object. Hence, a real, inverted and diminished image is formed. Let us now try out a numerical on concave lens. A concave lens has focal length of 15 cm. At what distance should an object from the lens be placed so that it forms an image at 10 cm from the lens? Also, find the magnification of the lens. Here, as we know, focal length of a concave lens is negative, so it will be given by f equal to minus 15 centimeters. Since concave lens always forms a virtual image on the same side of the object, the image distance is always negative. Therefore, image distance is equal to minus 10 centimeter. we are required to find magnification of lens and the object distance. We will be using the lens formula 1 by V minus 1 by U equal to 1 by F. Now rearranging the lens formula in accordance to our needs, we can write it as 1 by U equal to 1 by V minus 1 by F. Now substituting the values of V and F into the equation, we will have 1 upon minus 10 plus 1 upon 15 is equal to minus 1 upon 30. Therefore, the object distance turns out to be minus 30 centimeters. Thus, the object should be placed at a distance of 30 centimeters on the left side of the concave lens. Moving over to finding the linear magnification M given by the relation M equal to V by U equal to minus 10 upon minus 30 equal to 1 by 3. Therefore, the magnification turns out to be 1 by 3. The positive sign of magnification shows that the image is virtual and erect, and the size of the image is 1/3 the size of the object. Power of a lens. We know that a convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. Similarly, concave lens of very short focal length causes higher divergence than the one with longer focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of a lens is defined as the reciprocal of its focal length. It is represented by capital letter P. The power P of a lens of focal length f is given by P equal to 1 by f. The SI unit of power of a lens is diopter. It is denoted by capital letter D. If focal length f is expressed in meters, then power is expressed in diopters. Thus, 1 diopter is the power of a lens whose focal length is 1 meter. The power of a lens carries the same sign as its focal length. Therefore, the power of a convex lens is positive, and that of a concave lens is negative. Opticians prescribe corrective lenses indicating their powers. Let us say the lens prescribed by an optician has power equal to plus 2.5 diopters. This means the lens prescribed is convex. The focal length of the lens is 1 upon f, that means 0.40 meters. Similarly, a lens of power minus 2 diopters has a focal length of minus 0.5 meters. The lens would be a concave lens. Many optical instruments consist of a number of lenses. They are combined to increase the magnification and sharpness of the image. The net power P of the lenses placed in contact is given by the algebraic sum of the individual powers P1, P2, P3, etc. Therefore, in the form of a mathematical relation, we may write P is equal to P1 plus P2 plus P3 plus so on. The use of powers instead of focal lengths for lenses is quite convenient for opticians. During eye testing, an optician puts several different combinations of corrective lenses of known power in contact inside the testing spectacles frame. The optician calculates the power of the lens required by simple algebraic addition. For example, a combination of two lenses of power 1 diopter and 0.5 diopters is equivalent to a single lens of power 1.5 diopters. The simple additive property of the power of lenses can be used to design lens systems to minimize certain defects in images produced by a single lens. Such a lens system consisting of several lenses in contact is commonly used in the design of lenses of camera, microscopes, and telescopes. Why not take up a numerical to solve? A doctor has prescribed a corrective lens of power 1.5 diopters. Find the focal length of the lens. Is the prescribed lens diverging or converging? Here, power P is given to be plus 1.5 diopters. The formula that relates power and focal length is given by P equal to 1 upon F. Therefore, the focal length can be calculated by using the formula F equal to 1 upon P. Since power is in diopters, the focal length will turn out to be in meters. Substituting the value of P, we will have F equal to 1 upon 1.5 equal to 0.667 meters. In centimeters, we can write it as 66.7 centimeters. Therefore, the prescribed lens is a converging or convex lens because its power is positive. Dear students, we have learnt quite a lot today. Let us recapitulate our learning. A concave lens always forms a virtual, erect, and diminished image. In solving numerical problems on lenses, we use new Cartesian sign convention. According to the convention, the focal length of a convex lens is positive and that of a concave lens is negative. The lens formula gives the relationship between object distance u, image distance v, and the focal length f. The lens formula is expressed mathematically as 1 by v minus 1 by u equal to 1 by f. The magnification produced by a lens, similar to that for a spherical mirror, is defined as the ratio of the height of the image to that of the height of the object. M is equal to height of image h dash upon height of object h. Magnification produced by a lens is also related to the object distance u and the image distance v. It is given by the relationship m equal to h dash upon h equal to v upon u. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of a lens is defined as the reciprocal of its focal length. It is represented by capital letter P. The power P of a lens of focal length f is given by P equal to 1 upon f. The SI unit of power of a lens is diopter. It is denoted by the letter capital D. The net power P of the lenses placed in contact is given by the algebraic sum of the individual powers P1, P2, P3, etc. The mathematical formula can be written as P equal to P1 plus P2 plus P3 plus so on. So dear students, here is a task for you to do yourself. Practice making ray diagrams for different positions of the object. Solve more numericals based on lens formula, magnification, and power of lens from your textbook. So keep learning, keep practicing. Thank you.